Good morning, dear students. In this class, we are going to discuss about Werner's coordination theory and Sidwig concept. It is otherwise called EAN rule or 18 electron rule. And these are all the two concepts what we are going to discuss today. So Werner's coordination theory is a theory that explains the bonding in coordination complexes. So what is meant by coordination complexes? It is a class of compounds which contain a specific kind of bonds called a covalent coordination bond or simply coordination bond. So coordination bond is also a type of covalent bond, but the only difference is the electron sharing between two atoms in coordination bond is not mutual. That means one of the atom act as donor which gives pair of electrons to another atom, but the other atom just accept the electron, so it does not contribute anything to the bond. So it is a kind of donor acceptor type of bond, but there will be sharing of electrons between those two atoms. So this specific type of bonds are called a coordination bond. If a compound contain coordination bond, then it is called coordination complex. So the structure of coordination complexes was first explained by Werner's coordination theory, and Alfred Werner, who proposed this theory in 1898. So there are some postulates for this coordination theory, right? So it's a simple theory, but it very beautifully explains the typical bonding in coordination complexes. Let us take one of the complex as an example. Hexamine cobalt 3 chloride. So according to this theory, so look at the first postulate. The central metal atom in the coordination compound exhibits two types of valency, namely primary valency and secondary valency. So in hexamine copal 3 chloride, the central metal atom is cobalt. So every coordination complex has a central metal atom which acts as an acceptor of electrons. And the species which donate a pair of electrons to the central metal atom is called ligands. So in all coordination complexes, the bonding is between the ligands and the central metal ion. The central metal ion, according to coordination theory, has two types of valencies. One is primary valency, another one is secondary valency. So that is the ultimate concept of Werner's coordination theory. So central metal atom having two types of valencies called primary valency and secondary valency. So what is the difference between primary valency and secondary valency? The primary valency is actually ionizable valency. So if you dissolve a coordination complexes in any solvent, especially solvents like water, the primary valency will be getting uh, ionized, right? So primary valency denotes the oxidation state of the central metal atom. So primary valency means the oxidation state of the central metal atom. So look at the complex. So the structure of the coordination complex hexamine copal 3 chloride. So in which there are two types of bonds are there. One is a dotted bond and another one is thick bond. That dotted bond actually denotes the primary valency. So it can be ionized. It can be ionized and it is satisfied by the negative species like chloride, right? So primary valency is ionizable valency. That is the second postulate. The secondary valency is non-ionizable valencies, which denotes as a thick bond. Actually, it is the bonding between the ligand and the central metal atom. So secondary valency, like oxidation state, secondary valency has a specific number called a coordination number. For any metal atom, the coordination number is fixed. The structure of the coordination complex is uh, also established by the coordination number. So it depends on the coordination number alone, the coordination complex get its structure. Say for example, in this case, the coordination number is 6. So what is coordination number? The number of pair of electrons that is accepted by the central metal atom is called its coordination number. So it depends on the coordination number, a complex gets its structure, geometry, a fixed geometry, right? That's there in the next postulate. The ligands which satisfy the secondary valence of the metal ion exhibit characteristic spatial arrangements and hence have fixed geometry based on the coordination number. So secondary valency is otherwise called coordination number of the central metal atom, and based on the coordination number of the central metal atom, the geometry around the metal atom is fixed by the ligands, right? So every metal ion wants to satisfy both the primary and secondary valencies, right? So a coordination complexes to be stable, it's the central metal atoms primary and secondary valency to be satisfied, right? That is very important criteria. If one of the valency is not satisfied, the complex will uh, reduce in its stability. Okay, so these are all the postulates of a coordination theory of Werner, right? So it's very simple. I'm explaining it once again. So central metal atom ligands are there in the coordination complex. The central metal atom or ion which always have two types of valencies. One is called primary valency and another one is called secondary valency. The primary valency denotes the oxidation state of the central metal atom and it is ionizable valency, whereas the secondary valency denotes the coordination number of the central metal ion and it is non-ionizable. So in the typical structure of Werner, the primary valency is shown as a dotted line and the secondary valency is shown in thick line, right? So that's all about Werner's coordination theory. Now let us see the Sidwig concept of effective atomic number rule. It explains the stability of coordination complexes. So in order to get a stability, the central metal atom should satisfy a particular rule called effective atomic number rule. So what is meant by effective atomic number? The effective atomic number is the number that tells about the total number of electrons present around the central metal in a complex compound. The central metal ion must contain a certain amount of electron around it in order to get stability, and that number of electron is called the effective atomic number. So every metal ion has its own EAN. If the effective atomic number is satisfied, the number of electrons around the central metal ion uh, is obeyed or it just present as effective atomic number, then the complex will get more stability. So effective atomic number theory was the first theory that explained the concept behind the complex compound formation, and this theory was given by Sidwig. Let us see it a little more detailing. So Henry Sidwig observed that the metal present in any complex like metal carbonyl, for example nickel tetracarbonyl, has the same valence electron count as that of noble gas at the end of the row of the periodic table, of which the metal is a part. So it is referred to as 18 electron rule or EAN rule. So if you're looking at the central metal atom nickel here, the number of electrons around the nickel is equal to the number of electrons in the noble gas of the same series in periodic table, right? So that's why it is called its effective atomic number. Okay, say for example the noble gas series krypton, xenon, radon 36, 54, 86, these are all effective atomic numbers. So the metal ion which belongs to the particular series will try to attain the number of electrons present in the noble gases of that series, right? So that the number of electrons or the atomic number of the noble gases of that series is called its effective atomic number. So if you calculate the total number of electrons around the central metal atom in any coordination complexes, if it obeys the effective atomic number rule, that means that the number of electrons around the central metal atom uh, is equal to the atomic number of the noble gases of that series, then we can say that particular complex obeys the effective atomic number rule. Okay. So Sidwig's EAN rule tells about the stability of coordination compound. The metal ion in a coordination complex will continue accepting the electrons till the total number of electrons in the metal ion becomes equal to the atomic number of noble gas of that series. So if you're looking at the coordination complexes, the coordination number varies to metal to metal. Some metal ions get just one or two ligand binding with one or two ligand, accept only one or two pairs of electrons, and some go above 4, 6, etc. So which actually determine this, the coordination number? So it is actually determined by its effective atomic number, right? So until the effective atomic number is satisfied by the central metal atom, it will keep on accepting the electron pair from the ligand, and that is what the concept is. So what are the significance of effective atomic number? So the major significance of effective atomic number are listed below. The effective atomic number helps us to understanding why electrons when further apart from the nucleus are weakly bound it. The stability of the coordination compound is explained with the help of effective atomic number, right? So we can explain the stability of any complex using the effective atomic number. So in case of non-classic complex like that of metal carbonyl complex, the effective atomic number is more valid. Hence, this rule explains the stability, oxidizing and reducing character of the carbonyl compounds, though it is found to be invalid for most of the complexes. So it is seen to be valid for all the cases of carbonyl complexes. No ligand act as a 3 electron donor. It is a specific cases. We will discuss it little later, right? So okay. So this is important. How to calculate the effective atomic number for any central metal ion? So in order to find out the effective atomic number of a coordination complex, first you have to take the atomic number of the central metal ion, the complete number, atomic number, right? So from that atomic number, you have to reduce the oxidation number, the oxidation state of the central metal atom. So for example, if it is +2 means you need to reduce or you need to subtract the oxidation number from the atomic number. Then you have to take the coordination number multiple with 2. That will give the number of electrons donated by the ligand. So if you add that number with the atomic number minus oxidation state, then we get the effective atomic number. So that gives actually the number of electrons around the central metal atom, right? So this is how we can calculate the number of electrons around the central metal atom. The central metal atom already has its atomic number of electrons. So while forming the oxidation state like +1, +2, etc., it just releases some of its electrons, loses some of its electrons. That's why we subtract that oxidation number. Then this coordination number, according to its coordination number, the number of electrons, pairs of electrons given by the ligand, right? So each coordination number or each ligand gives pair of electrons to the central metal atom. So that electrons you have to add. So if you add sum of all the electrons given by the ligand along with the atomic number of the central metal atom, then we get the effective atomic number. So EAN is otherwise simply said as EAN is equal to Z minus X plus 2NL, where Z is atomic number of the metal in the complex, X is oxidation state of the metal in the complex, and N is number of ligands, L is equal to number of coordination bond formed by the ligand, right? So this is how we can calculate the total number of electrons around the central metal atom, right? So I'm explaining it once again. The central metal atom initially having its atomic number of electrons. While forming its oxidation state, it loses some of its electron. That is X2 that you have to subtract from the atomic number. And due to the coordination bond, due to the bonding of ligand with central metal atom, it gets certain number of pairs of electrons that you have to add with the number of electrons around the central metal atom. So thereby we get the total number of electrons around the central metal atom in any complexes, and that number is called EAN. Let us see some example. Look at the metal carbonyl, iron pentacarbonyl. So oxidation state of iron in iron pentacarbonyl is 0. Most of the metal carbonyls, the oxidation state of central metal atom is 0. So we don't need to subtract any number from the atomic number. So atomic number of iron is 26. So carbonyl CO, it's a monodentate ligand. That means it donates only one pair of electrons to the central metal atom. So there are 5 carbonyl groups are there, carbonyl ligands are there in iron pentacarbonyl, right? So through carbonyl groups, 10 electrons are donated to the metal atom. So initially it has 26 electrons plus 10 electrons are donated by the ligand. So totally the number of electrons around the ion in iron pentacarbonyl is 36. And if you're looking at the periodic table, the 36 is the atomic number of the noble gas argon, which is there in the 3D series. So last element of the 3D series, right? So that means here in the iron pentacarbonyl, iron having its atomic number of effective atomic number of electrons, that is 36. So we can say this particular carbonyl obeys effective atomic number rule. Right? One more example: hexamine iron 2. Hexamine iron 2. So oxidation state of iron here is +2. So coordination number is 6. All the amine ligands are monodentate. So atomic number 26. You need to subtract the oxidation number 2. So 24. So number of electrons donated by 6 ligands is 12. So 24 plus 12, 36. So 36 is the effective atomic number of iron. So this complex also obey the effective atomic number rule, right? So 18 electron rule, it's very similar to effective atomic number rule, but the difference between EAN and 18 electron rule is, in EAN case you are calculating the total number of electrons around the central metal atom. In 18 electron rule, you just calculate only the valence electrons, right? You just remove the core electrons. Instead, you just calculate the valence electrons. So if the valence electrons, total number of valence electrons in around the central metal atom is 18, then we can say the 18 electron is obeyed, right? So what you have to do, instead of taking the atomic number of central metal atom, you need to take the valence electrons of central metal atom. Let's see the same example: iron pentacarbonyl. The valence electron in iron is 8, just 8. So in EAN case, you take the atomic number. Instead here, you take the valence electron, right? So iron is actually 26. So 26 means it has 8 valence electrons. So 8 valence electrons, right? So actually 4s2 3d6, 4s2 3d6 are the valence electrons. So 2 plus 6, 8 electrons are in the valence shell. Valence shell, 8 electrons are there. So oxidation state you need to subtract, but the oxidation state here is 0. So no need to subtract any number. So electrons given by the carbonyl ligand is 10. So 8 plus 10 is equal to 18. So number of electrons 18, right, in the valence shell. So 18 electron rule is obeyed, right? So they can ask like this. They give some coordination complexes and ask you to check whether the coordination complex obeys 18 electron rule or EAN rule. You need to calculate accordingly. If they ask 18 electron rule, you need to take the valence electron of the central metal atom. If they ask for EAN rule, then you need to take the whole atomic number of the central metal atom. First you have to subtract that its oxidation number, then you have to add the electrons donated by the ligand, and the sum to be equal to its effective atomic number, or 18, number 18, if you calculate with valence electron. That's it, right? We'll just try these complexes at home. So just take, first you just have to take the atomic number. uh, just check both EAN and 18 electron rule for all these complexes, right? So if it is not obeyed, just explain it's not obeyed. That's it. Okay, right? Thank you. There are some complexes, not necessarily all the complexes to obey AN or effective atomic number rule. Some complexes are not obeying the AN rule, that you have to find out by calculating the AN rule according to the formula. AN is equal to Z minus oxidation state plus 2 into coordination number, right? So thank you very much for listening. So we shall meet in the next class. Thank you.